Okay, this is in fact chapter 11 in the textbook, and sometimes, in fact, one time one of the students who knew what chapter 11 is, he said, yeah, we are bankrupt at this point in semester, and you are studying the most important subject in all mathematics, sequences. And yeah, sequences, that's like the first door to higher mathematics. And I can tell you that, say, at University of Minnesota, which I know, they even invented the course to, by having in mind that Calc 2 does not really go through this thing in a decent way, and students need more, so they invented some course by that name, sequences and series or something. Uh, Anyway, so I will try to give you some ideas on sequences and series. It looks so simple at the beginning. In fact, it is simple. In my opinion, it's not that hard. But since it becomes more conceptual, and understanding, say, when it comes to series, for example, the convergence of a series and things like that, it might be a little bit not hard to understand. I don't know what to say. It depends on the person, and if you try to go deeper and think deeper, then you will understand. You say, spend some more time thinking about what's going on. But again, this book, and I guess no calc book, does a decent job in this area. But well, we need that. And to be honest with you, I got interested in studying mathematics myself by two things. The first was the idea that maybe I mentioned when I was discussing improper integrals, the idea that geometric shape which looks unbounded has finite area. And also this one, series. Taylor series, and back then Taylor series was used to calculate value of certain functions, which was like a mystery for me. How could a simple calculator find sine of, say, 35.2 degrees? What is it? Is there like a table in that calculator? And if there is, then that table should be an amazingly huge table. But there is no such table. In fact, these days they use different algorithms, but back then I remember somebody told me that they used Taylor series in those old calculators to calculate the value of transcendental functions like sine and cosine and ln and e to power x and blah blah blah, other things. Okay, so we will learn something about sequences, and then we end up with series, and that is what I'm trying to say. We will see that, for example, e to power x, a transcendental function, is in fact, you can write it as an infinite polynomial. That's interesting, an infinite polynomial. And we can truncate that polynomial at some point and just use that as an approximation to e to power x. Well, that's called Taylor series, and when you truncate that, it's called Taylor polynomial. But for functions like sine and cosine, that works amazingly. So if you write down those for sine and cosine, let's write this one first. So this one is in fact a series like this. Say k from 0 to infinity, x to power k over k factorial. So this is in fact 1 plus x squared over 2 factorial plus x 3 over 3 factorial plus x 4 over 4 factorial plus dot, dot. So if I write it, it will be x plus 1 over 2 factorial x squared plus 1 over 3 factorial x 3 plus 1 over 4 factorial x4 and dot, dot, dot. So it is a polynomial of degree, it's like a polynomial of degree infinite, right? Well, what does that mean? I'm just giving you an intuitive idea. Now, if I truncate this at some point, say x to the power, say 30, that's a lot, I know. Then it probably can approximate the value of e to the power x for large enough x. There are ways to do that without using that many, but let's look at this. Now, one other thing. So if I want to calculate this, if I use, say, up to x to the power 30, even if I have a calculator which has just 4 operations, not even square root, I can do that. I can find the value of e to the power x for any x. Yes, that's hard, it takes some time, but theoretically I can do that. So if I have large x, then I just go on and on and on. Yeah, it takes time. It might be x to the power 10 million. But that is x to the power 10 million. How do you find x to the power 10 million? You multiply x 10 million times. And if you have a calculator which has 4 operations, you can do that. You can do that with the simplest calculator. So what this thing does is it reduces this transcendental function into this, into a polynomial that is a lot more manageable, and the computer understands that. The computer understands what? Just addition. The computer has addition. Then you define subtraction and multiplication and division using just that addition in a sense. So you can see that it's just those 4 operations, nothing else. Polynomial is just 4 operations. Not even square root, not even anything to power like a rational power. Everything is amazingly nice, and every x is to some integer power, positive integer power, or non-negative integer power, say. So, now this perhaps you might say, okay, if x is too large, which is true in fact, for x large you need huge number, so the degree that you need is maybe too large. Now, if let me write sine theta or sine x, we encountered this thing in previous lecture, in fact, when we were finding the area of differential of area using the formula which has cosine in it, and I said cosine sine d theta is approximately theta. Now you will see that. The Taylor series for this one is x minus x to the power 3 over 3 factorial plus x to the power 5 over 5 factorial minus x to the power 7 over 7 factorial plus minus, and this one has the odd degree. And it is amazing because sine x is an odd function, and every one of them has odd degree. So this is an odd function, in fact, on the right side. And you can try on your calculator. I might, again, if I have time, I will give some lecture just using Mathematica, for example, and show you lots of things. And one of them is this: if you just pick this tree, truncate, and try to find sine x for x between 0 and pi over 4. And that is all we need for sine of theta. If you have sine theta between 0 and pi over 4, you can find sine theta for any theta. Why? Just think. And for angles between 0 and pi over 4, use this is, in fact, this should be in radians, no degrees anymore. We are just using radians here. And that is that up to 5 gives you an amazingly nice approximation. So amazingly nice approximate value between 0 and pi over 4. You don't have to, if you have an angle which is 10 million degrees, you can bring it down to something between 0 and pi over 4. Or related, I'm not saying 0 and pi over 4, but related to this. In fact, you can bring it down to something between 0 and pi over 2, but it is symmetric with respect to this point, pi over 4. So, anyway, and the same is for cosine. So this is like the Taylor series or the Maclaurin series, as they say. Cosine x will be 1 minus x squared over 2 factorial plus x4 over 4 factorial minus x6 over 6 factorial plus dot dot dot. And you see all of them have degree, say, even degree. Even this is x to the power 0. Well, you can say 0 is even. That's okay. So anyway, this is also an even function. So even, and that's an even function. Now, I'm not going to write down tangent. Tangent is just not so nice. Even for this one, if we just pick these 3, that's it. That is all you need for angles between 0 and pi over 4. And you can find value of those sine and cosine for any angle. It's an amazingly good approximation. So the error is very small. Okay, so that's how Taylor series and series, in fact, can help us. What it's in numerical mathematics. One place is numerical mathematics. Another place you can just look at this and say, okay, if x is small, say, then x to the power 3 is very small. X to the power 5 way smaller, small. So sine x is approximately x when x goes to 0. How about cosine? You say, yeah, if x goes to 0, x is very small, then cosine x is approximately 1. Right? So you can say lots of things about some functions in theoretical sense if you have the Taylor series. Okay, so, but all of this starts with sequences. One thing is you will see that yourself that the sequences and series are sometimes confused by students. Since they are related, in fact, the series and the, say, sum of a series and blah, blah, blah is defined using sequences. That's why I said sequences are essential in this, say, chapter, and also, as I said, like the first door into higher level mathematics. So let me start with sequences. You have some sequences in pre-calc. So you have seen 2 types, maybe arithmetic. Arithmetic, I think it's. I think it's arithmetic. Right, so that is, you start with something, say 2, and then you add the same number to this. So 2 plus 5, 2 plus 5 plus 5. 2 plus 5 plus 5 plus 5. So in fact you're adding 5 times something. And n starts at 0, 1, 2, dot, dot, dot. So your sequence has the general term, this is called general term. The general term is written in terms of, usually we use n, so n, m, p, something like that. Usually n, m, I, j. You can use anything, but most often in mathematics, when you use n, in a sense, you're talking about an integer. So it has an index here, and this index somehow appears in the formula. So if I write a n equals 2, it means that it's a constant sequence. It is just 2, 2, 2, 2, 2, 2. So in fact, it's like saying 0 times n, right? So n appears in the formula. And it's important where it starts. Does it start at 0 or it starts at 1? Does it start at 5? Yeah, it can start at 5. Does it start at negative 10? So this is also important. Where does it start? So it's important where it starts. Does it start at 0? Does it start at 5 or negative in, say, 500? Something. Okay, so this is in fact the general formula for arithmetic sequence. So if I start with A0, then the second one is A0 plus D, then A0 plus 2D, and dot dot dot. So in this situation, AN will be A0 plus, if I start at 1, usually they start at 1, N minus 1D, and let's start at 1, because A0 is already here. So 1, 2, dot dot dot. So be careful again. Where does it start? How do you know that? Look at this. If N is 1, this is 0, you will get A0. So most often if you check the first term in the sequence, you can tell where it starts. So check the first one in the sequence. If you are not satisfied, check the second one. Second one will be 2. If I put 2 here, it's 2 minus 1, which is 1 times D. So it is A0 plus D, and so on. So to find out where it starts, if the sequence is given to you in this form, not this form, then you can find out the starting point of this N. Now, it's interesting. You might say the one other thing is how to find the sum of a bunch of a sequence. So you might say, can you find the sum of this? Well, let's try. Let's try. So what is sum? The summation notation which you have seen in the Cat 1, say for integrals. So n starts at say 0, and let's end it at some point, say 40. Okay. So this is an. So that is what I'm trying to find is 0 to 40 of 2 plus 5n. Okay. So I have to add this thing. So one thing is how to add this thing. In fact, in a sense, was discovered. They say that that's a nice story. They say that Gauss, in fact, discovered, and he was punished for doing that. I don't know, that might be just children's story, but it's interesting to know how he did that, or did he do that, or that was like the story behind what he did. In fact, Gauss is considered one of the greatest mathematicians ever, and at least in the past they called him the Prince of Mathematics. So I don't know what Prince, King, or whatever it is. So that's how they say how Gauss did it. They say that Gauss it was in like maybe elementary school, and the teacher wanted them to keep quiet. So the teacher was mean, and the teacher told them to find this sum: 1 plus 2 plus up to 100. And she thought that's okay. Now they don't talk, and they just add the numbers. And Gauss apparently in a few maybe minutes said, "Yeah, I solved it," and the answer was correct. And the teacher punished Gauss. But that's how he did it. He said, "Okay, if I write this backwards, this way, 1 plus 2, so this is 99, and this one will be 99 here and 100. So if you write it backwards, this is 101, and the last one is 101. So how many 101s do I have here? I have 100, 101. So 100 times 101. And I have added them twice. So divide by 2. So that's 50 times 101. So it is 50, 50, is it? Okay, so then, and he found it, he calculated this and he was punished, but the answer was correct. And but what did he do? He wrote this thing backwards and added, wrote it backwards and added. And it's interesting that it really works. If you do it like that, it works. And how is it related to that? Well, very simple. If I can write it like this, I can write it as sigma n from 0 to infinity, separate this, just 2. Okay? And then I can write the 5 outside, the 5 is multiplied by each one of them, n from 0 to 40 n, right? And from 0 to 40 n, and say, okay, this is 41 in fact, 41 twos. From 0 to 40 is 41, it's not 40. From 1 to 40 is 40. From 0 to 40 is 41 terms, remember that. Because from 1 to 40 is 40 and I'm adding another one. So that first part is 41 times 2, and this one is 5 times what? It's like this, except it starts at 0. Well, like we can ignore 0 because n0 is 0 and nothing happens. So I can ignore 0 and I said, in fact, that is 1 plus 2 plus dot 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 plus 40 and write it backwards, 0 dot 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 up to 40. And I have 41, 41 dot 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 41. So I have 40 times 41 divided by 2. Do you see a trend here? So this is 5 times this. 5 times 40 times 41 divided by 2. So that is, in fact, the result. And 40 divided by 2 is 20. So I will get this. So the result is this. 41 times 2, that is 82 plus. This one is 40 divided by 2 is 20 times this is 100, right? So plus 100 times 41, and I have 82 plus 4100. If I'm correct, that's with 4182, right? So that's the sum, say. And so there should be something related to this, right? Finding this thing for any n. So let me write it here. Okay, so what is sigma n? Well, let me write, well, that's okay. So n starting at 1 going to something n. Right? I should have said k. Yeah, let's write k because it's much nicer to write k here and n here. So k from 1 to n, k. So this is 1 plus 2 plus dot, 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 up to n. And I'm starting at 1, not 0. There's no point in starting at 0 because 0 plus anything is 0. And anything is that thing, sorry. That 0 doesn't affect the sum. So let's start at 1. So what should I do? Let's write it backwards. 1, 2, dot, 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 n. Add them. I have n plus 1, n plus 1. How many n plus 1s do I have? N times n plus 1. And divided by 2. So this is in fact 1/2 n times n plus 1. Okay, so that is k from 1 to n of k. Okay. So that is the sum of the first n nitron numbers. So let's see if I can use it in finding, so let me write this thing up here. that sigma k from 1 to n of k in fact is 1/2 n times n plus 1. There's also another way to say this thing. What is that? What did I do? In fact, it was like the first one plus the last one times number of terms divided by 2. The first one plus the last one times number of terms divided by 2. That's another way to say this. Now, we will see that for any arithmetic sequence, that is what happens. So that's what we have here. Now, let's try this. Sigma k from 1 to n, a0 plus k minus 1 times d. So this is a0 plus a0 plus d plus a0 plus 2d up to a0 plus n minus 1d. See, so the general term in fact is this, when k is n, or k is k. So this is the general term. Okay, so let me decompose this thing and try to use that formula over there. So I can decompose this in this form. So I have just a0, k from 1 to n. This means add a0 n times, right? Is it a0, 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 a0? a0 is added to itself n times. Then I have a k times d. So I have a k times d, and k is part of this thing. So I have d times sigma k from 1 to n. Okay, and then I have minus d, minus sigma k from 1 to n, k from 1 to n, simply just d itself, right? So this is n a0, remember that's just n a0s, plus d times, what do I have over there? 1/2 n times n plus 1. And how many d's do I have here again? Nd minus nd. Okay, so by using this formula discovered by Gauss and just simple understanding, just simple things, simple facts, that if I add a number to itself n times, I will get n times that number. So let's see if we can simplify this thing to some extent. I have this one is 1/2 n squared plus 1/2 n. So what do I get here? Let me erase this and see what I get. So I have n a0 plus d times 1/2 n squared plus 1/2 n minus n, right? 1/2 n minus n will be minus 1/2 n. So I have n a0 plus d times 1/2 n squared minus 1/2 n. So it is n a0. I can write it in this form: 1/2 n times n minus 1, right? N times n minus 1, and I can live it like this. I can say, okay, that's it. That is the formula for, or I can maybe, let's see if I can do something. If I move this 1/2 n outside, because I have an n here, right? So if I write it as 1/2 n, then I will get 2a0 here plus n minus 1 d. to a0 plus n minus 1d, right? This is a much nicer formula. So let's stick with this one than this one. So let's say that this sum, what was that? The sum of the n terms, sigma a, k from 1 to n, is this, for arithmetic sequence. And ak is a0 plus n minus 1 times d. Okay, let's analyze this further. This is amazing that I said that you can write it in a much nicer way. 1/2 n. This inside is a0 plus n minus 1 d. Right? What is this? a0 plus a times n minus 1 d? So this is the first term. This is in fact a1. Remember, a1 is a0. Yeah, you said G. Whatever. But that a0 is just a symbol, let's say. And this is the first term, and this is the last term. So it is the first term plus the last term times n divided by 2. And that's what Gauss did, right? First plus last times n divided by 2. Right? First plus last times n divided by 2. So that's like Gauss's formula or Gauss's method. So if you are given an arithmetic sequence, which doesn't happen too often, it's just playing games. But if you are given something like an arithmetic sequence, maybe just in number theory, you might get things like that. And that is very simple. So if you are given, say 2, 4, let's add 3, right? Not 2. Then 2 plus 3 is 5, then 3 is 8, then 11, and where does it go? Say 11, 14, and 17. Let's stop here. Is it correct? 3 plus this one is 5, plus this one 8, plus this one 11, plus this one is 14, plus 17. So if I want to add them using this formula, which is in fact Gauss's formula, I simply say I know this is 1/2, 1, 2, 3, 4, 5, 6 times 6 times the first one, 2 plus 17. Okay. So that's it. So you have the result. So if you are adding some numbers and you see some, if it is like an arithmetic sequence or something related to arithmetic sequence, then it's good to use that formula, that simple formula of Gauss. Now, okay, that's the kind of sequence that is not that much useful for us. Let's go for another sequence, geometric sequence. Geometric sequence. Now the geometric sequence starts with an a0, which is not 0. Then you multiply it by some r. Then again, and you start at some point. And y n minus 1, that's a0. So, well, why should I write a0? Let's write a. Because then you get confused about this. There's no a0. No, why did I use a0 for the other one? So this is like the first term, the second term, third term, and this is the nth term. Remember, look at this. 2 is 1. 3 is 2. 4 is 3, and just go on. N is n minus 1. So, the geometric sequence is crucial So let's say I have 1/2 multiplied by 1/3. So I have 1/2 times 1/3, 1/2 times 1/3 square, 1/2 times 1/3, 1/2 times 1/3 to the power 4, dot, dot, dot. So that's geometric sequence. And how can we find well, there's one way to do it, which is not that hard. There are two ways to do it, but let's do it using arithmetic sequence. And bear with me. Bear with me. Let's say we want to find this sum, which is sigma a r k minus 1, and k goes from 1 to n. Okay? So what should I do? So this is in fact a plus ar plus ar squared, ar n minus 1. Now this is what I will do. I will multiply this by r. Rs will be ar squared, ar3, ar n minus 1, ar n. Okay? Now, this guy here, from here to here, look at this. What is it? Ar, I'm talking about this. Right? That's the same thing. So this is in fact S minus A. That is S minus A, right? So I have R S equals S minus A plus ARN. I'm trying to find S, so solve for S. If I solve for S, I can take this one here and that one to other side, and I have A minus ARN, and there's a reason I'm writing it like this, you will see, equals S minus RS, okay? S minus RS. So let me write this here, up here. So I have A times 1 minus Rn equals S times 1 minus R. And that gives me S is A times 1 minus Rn divided by 1 minus R. Usually we call it Sn, in fact. So that's the sum of the first n terms of a geometric sequence. Okay, so the first n terms of a geometric sequence has this sum. Let's find that for example. I had 1/2, then the second one was 1/2 times 1/3, then it was 1/2 times 1/3 squared, and plus 1/2 times 1/3 to the power, say, 26, say. And nothing else is given to you. So we have to identify certain terms. So I need A, first term, 1/2. I need R, from first to second, it's multiplied by 1/3. Now I could have written 1/2 and 1/6. So you have to divide this by this. Divide the second one by the first one. So how do you find that R is A2 over A1. Simply that. Just write down the two terms, divide the second one by the first one, and you have R. That's it. So, well, this is written so I know what R is. Then how many terms do I have? Remember, this is n minus 1. This is n minus 1. So n minus 1 is 26, and this gives me n is 27. Right? So S27 will be A 1/2, 1 minus 1/3 to power 27, and divided by 1 minus 1/3. Okay, so simplifying this is in fact 2/3, and it will give me 1/2, 2/3, that is 3/4 times 1 minus 1/3 to power 27. What do you think this is? Well, you can just write it like that and leave it. But 1/3 to power 27, 3 to power 27 is a huge number. And 1/3 to power 27 is almost 0. So this guy goes away. So it's almost 3/4. It's almost 3/4. Isn't it amazing? If I continue writing this to infinite, I'm getting close to 3/4. Because it is 3/4 times 1 minus something tiny. It gets tiny, almost 0. So S infinite is in fact 3/4. This is where I guess if you think more about this thing, if you're interested in understanding this deeply, you can look at, in fact, geometric series as n goes to infinity. And you have the R for this geometric series is a number which is less than 1. Or between -1 and 1, in fact. Okay, so let's look at that Sn and try to understand what's going on with the Sn. Because we are more interested in S infinity. So what is S infinity? S infinity is defined to be a limit of Sn as n goes to infinity. So what do you think that is? It all depends on, so S infinity will be limit of this guy here A times 1 minus Rn over 1 minus R. Remember, everything constant comes out of the limit. So the A over 1 minus R comes out, and I'm left with limit of 1 minus Rn. And so it all depends on this thing, in fact, limit of Rn, right? Because limit of 1 is 1, so it comes down to limit of Rn. So what is the limit of Rn? One can prove using rigorous mathematics that this is 0 if R, absolute value of R is less than 1, that is if R between -1 and 1. And you can guess, between -1 and 1 is the rational number, right? And a rational number like that 1/3. 1/3 or any rational number, as you raise it to some power, it gets smaller and smaller and smaller. No matter if it's positive or negative, it gets smaller and smaller. So, and it gets closer and closer to 0. And it is infinite if R is bigger than or equal to 1. It's infinite if it is bigger than or equal to 1. Now, even if it's 1, no, that is, yeah, that's correct. So, 1 to power, let's say 1 to power n, let's say it is bigger than 1. At 1, yeah, at 1 is 1. So it's not, but it's not 0. At 1 it's not 0. So 0 happens only here. what I was thinking about the series, that's when you get confused. So this one is in fact 1 when r is 1. When r is -1, there is no limit. When r is -1, there is no limit. When r is bigger than 1 or less than -1, there is a limit. That is infinite, some kind of infinite saying. But, or let's say it's not convergent. So let's say it's not convergent. So, well, we need that to be 0. Okay, anyway, so when r is less than 1, absolute r is less than 1, we can say that this is in fact convergent. When absolute r is less than 1. Now, why I do not choose r equals 1? Because of this. What is r equals 1? R equals 1 is a plus a plus a plus a. That's infinite, in fact. So for r equals 1, it is divergent. And it's a divergent when absolute r is bigger than or equal to 1. But we can find the limit when r is when r is less than 1. So the limit will be this: s infinity will be a over 1 minus r when absolute r is less than 1. Okay, so that is limit when an infinite geometric series, the sum of an infinite geometric series, or a sum of infinite geometric sequence. And so let's do some examples here. Examples. And so if I start with this, what was that? 18. And so on. And you know that it is geometric series. So one thing you should find is A. Look at the first one. Don't try to count and say. Don't try to write down the general form. No, don't write the general form if it is given like this. The first one is A. Then divide this by this. That's all you need. That's all you need. So S infinity is 1/2 over 1 minus 1/3. And that we found it was 3 over 4. So that sum is basically 3/4. Okay? And let me give you 2 more examples here and then stop. What if I am given something like this, sigma k from 0 to infinite 1/2 to power k. And you say, oh, okay, I know that is 1/2 divided by blah, blah, blah. No. Whenever anything like this is given to you, write down the first and second terms, at least. Which is okay, in fact, you just need that. What is 1/2 to power 0? It's 1, it's not 1/2. Then it is 1/2, then it is 1 over 4, and so on. So what is A? This is A. What is R? It is 1/2 over 1, which is 1/2. You could tell from here. So S infinity is 1 over 1 minus 1/2, which is 3. Okay, that is in fact 2. Let's find this when k starts at 1. when k starts at 1, then I have 1/2 plus 1/4 plus 1/8 and so on. So this is A again, and R is 1/4 divided by 1/2, which is 1/2. So S infinity in this case is 1/2 1 minus 1/2, which is 1. So be careful when you're finding a limit of a geometric series, be careful. Look at the first term, look at the first term. Fine, look at the first term. Or find the first term. First term, first term, first term. Don't tell me that I didn't tell you, okay. This first term is annoying, so write down at least 2 terms in that series and look at the first term, and that comes here. Then find R. Don't worry where it starts already. It doesn't end. In fact, it goes to infinity. And another thing is interesting, that this is in fact 1. So that series that's infinite, and it gives you the number 1. Okay, so let me stop, and we will go deeper into sequences.